All right, today we're putting on our staff engineer hats. We're going to tackle a massive challenge, designing a global news aggregator, just like Google News, completely from the ground up. We're talking about a system that has to process thousands of publishers in real time and serve a personalized feed to, get this, 500 million daily users. The scale here is just immense. So let's dive right in. So here's our game plan for today. We're going to start with the blueprint, laying down the core rules. Then we'll build the system in two big phases. First, figuring out how to collect all the news, and then how to serve it up. After that, we'll do a couple of deep dives, really stress testing our design for performance and those crazy traffic spikes before we pull it all together and reveal the final architecture. Every great design starts with a solid blueprint. Before we even think about code or servers, we need to know exactly what this system has to do and what kind of data we're working with. These are our core requirements and entities. Okay, first, the functional requirements. This is the stuff the user actually does. They need to see a feed, they need to scroll through it forever, and when they see something they like, they click it and go to the publisher's site. Seems simple, right? Well, the non-functional requirements, that's where the real engineering puzzle is. We have to scale to 500 million daily users. The feed has to load in under 200 milliseconds. And, this part is absolutely crucial, we have to prioritize availability over consistency. Now, what does that mean? It's a huge trade-off. It means we would much rather show a user a feed that's, say, a minute old than have them see a loading spinner because we're trying to get the absolute freshest article. Uptime is king.
So what are the fundamental building blocks here? It really just boils down to three main things. We've got the publisher. Think of them as the source, like the BBC or the New York Times. They create the article, which is, the actual news story. And then we have the user, the person reading it all. Just understanding how these three things relate to each other, that a user from a specific region wants to see articles from certain publishers, that's really the key to everything we're about to build.
All right, blueprint is in hand. Let's move on to our first major phase, actually collecting the news. How in the world do we get a constant real-time fire hose of information from thousands of different sources all over the globe and get it into our system?
The magic here is a technology that's actually kind of old school. RSS, which stands for Really Simple Syndication. It's just a standardized XML format that pretty much every publisher on the planet already provides. And for us, that is a huge win. It means we don't have to build thousands of custom web scrapers or special APIs. Nope. We just need one simple system that sends a standard GET request to a publisher's RSS feed, and boom, we get back a perfectly structured list of all their latest articles. So simple.
So here's the workflow, and this just runs in the background 24/7. First, our data collection service queries our database to get the list of all the RSS feeds. Second, it goes out and pulls every single one of those URLs, pulls down the article data, and downloads the thumbnail images. Third, it saves the article's text data into our database, and the image files go into a separate object storage service, like Amazon S3. Now, we do this for a super important reason. We could just link to the publisher's image, right? But what if their server is slow or goes down? It would break our feed. By hosting the thumbnails ourselves, we guarantee that speed and reliability for our users. So we're collecting news around the clock. That's fantastic. But that's only half the battle. Now for the other side of the coin, getting that news into the hands of millions of users. Let's talk phase 2, serving the feed. Let's just trace a single request to see how this works. A user opens the app. Their phone sends a request to our API gateway. That gateway routes it to our dedicated feed service. The service then queries the database for the newest articles that match the user's region. It formats them nicely and sends them right back. You'll notice we have two separate services here, one for collecting data and one for serving it. That is a deliberate key design choice because they have totally different scaling needs. So we have a basic system, and hey, it works. But we have to ask a critical question. With this simple design, what happens when new articles get published while a user is already partway down their infinite scroll? This is exactly where our simple little approach starts to completely fall apart, and it leads us right into our first deep dive. Our basic system might be okay for 1,000 users, maybe, but it will just crumble under the weight of millions. It's time to level up our architecture so we can handle real-world scale and actually deliver that sub-200 millisecond performance we promised. Okay, let's fix that broken infinite scroll. The simple way to do it is called offset pagination. It's like asking a librarian, give me page 2 of the results. But if a new article gets added to the top of page 1 while you're reading, everything shifts. You ask for page 3 next, and you end up seeing articles you already saw. It's a mess. The professional solution is cursor pagination. This is like telling the librarian, give me the 20 articles that come after the one with this specific ID. That ID is a stable anchor. It doesn't matter how many new articles are added to the top, you will always get the correct next set. It guarantees a perfect, seamless scroll every single time.
Now let's talk about speed. Look at this number, 500 million. That's how many times a day users are going to open our app and expect an instant feed. Hitting our main database 500 million times a day is it's a non-starter. The database would literally melt. It's a recipe for a slow, frustrating system that totally fails our latency goals.
So, how do we get fast? The answer is caching. Now, a good solution is to stick a Redis cache in front of the database to store results for a few minutes. That helps, but what happens when the cache is empty? That first user still has to wait for a slow database query. A great solution is to be proactive. We pre-compute the entire news feed for each region, and we just store it directly in the cache. When a new article comes in, our system doesn't just write it to the database, it also instantly updates that cached feed. That way, the user's request always hits a hot, ready-to-go cache, and the response is blazingly fast. Okay, our system is now fast and it's consistent. But what happens when major news breaks? An election, a natural disaster, some massive global event? Our traffic isn't just going to increase, it's going to explode. This right here is the ultimate stress test. And this brings us to the key insight for scaling a system like this. News consumption is regional. It just is. Most users in the US want US news. Users in Europe want European news. This means we don't have to build one single monolithic system to serve the entire planet. We can actually partition our architecture into smaller, independent regional deployments. A massive traffic spike in Asia won't even be noticed by the system serving North America. It's brilliant. Partitioning helps a lot. But it doesn't solve everything. A single regional system might still have to handle, say, 10 million concurrent users, all refreshing their feeds at the exact same time. We've already decided that all of these requests are going straight to our cache. So the new bottleneck is the cache itself. How do we scale that? Well, a single beefy Redis instance can handle about 100,000 requests per second. That's pretty impressive, but we need to handle 10 million. So let's do some quick back-of-the-napkin math here. 10 million users divided by 100,000 requests per second is 100. We need the power of 100 Redis instances for that one region. The solution is something called read replicas. We just create dozens, or in this case 100, read-only copies of our main cache, and we spread the load across all of them. Here's how that works. It's pretty clever. All the write operations, like when a new article is added to the cached feed, they all go to a single master instance. That master then automatically replicates, or copies, the new data out to all of its replica instances. Then, that massive flood of read requests from all the users gets distributed evenly across all of those replicas. This architecture lets us absorb basically any amount of read traffic just by adding more replicas. And with that, all the pieces are finally in place. Let's take a step back and just admire the robust, scalable, and high-performance system we've designed together. This quote right here really captures the beauty of our final design. Our regional architecture gives us fault isolation, meaning a problem in one part of the world doesn't cascade and take everything down. And by serving these pre-computed feeds from our replicated cache, we can get response times well under our 200 millisecond goal, probably closer to 50 milliseconds in reality. So let's just recap the 4 key decisions that really made this all possible. For ingestion, we used a simple, super reliable RSS polling service. For the user experience, we implemented cursor pagination. For latency, we used proactive, real-time caching. And for scalability, we combine those regional deployments with read replicas to handle just about any traffic spike you can throw at it. You know, we've built an incredibly powerful, scalable delivery pipeline, but it treats every single user exactly the same. We've mastered the how, the engineering of delivering the news, but the next and maybe even harder challenge is the what. How would you design the machine learning systems, the recommendation engines needed to sift through millions of articles and find the 10 that matter most to one specific person? That's where system design meets data science. And, well, that's a whole other challenge for another day. Thanks for joining me on this one.